everyone, it's Mrs. Suderman. Here's a video on factoring using the greatest common factor, difference of two squares, and a little bit of trinomials as well. So this is what your worksheet looks like, and you see at number 1 we have what is the greatest common factor of a polynomial. If you would like to write this definition down, or you can wait until you get your worksheet, which you could also print off of the website as well. But let me read it to you. It's the product of the greatest integer and the greatest power of each variable that divides evenly into each term. And if you want to be able to read that, you can check it out on page 331 of our textbook. Okay, so let's look at a few examples. And you may have seen the greatest common factor before, but let's look at number 2. So we have 2x cubed y minus 12x squared y to the fourth. So first what we want to do is look across and look at the integers. So we've got 2 and 12. And between both of those, what is the largest integer that we can divide out of both? It's 2. So first we'll just jot that down. So there's 2. And then now we can look at the x's, and we see that we want to look at the highest power that's available in both. Well, we have an x cubed and an x squared. So that means that there's an x squared available in both of them. And then now we can consider the y values. There's a y to the first power. Oops. Whoa. A y to the first power, and then a y to the fourth power. So between both of those, the highest exponent that we have is just y to the first power. So there's our greatest common factor, but we're factoring out the GCF. So in parentheses, we're going to write whatever was left over. So for the 2x cubed y, we've taken out the 2. For the x cubed, we've taken out the x squared. So that means we only have an x left over. And then we've got y to the first power, and we've already divided out the y. So there's our x minus 12 divided by 2 is 6. We have an x squared divided by an x squared. Well, that's just 1. We've already taken out the x squared. We also have y to the fourth divided by y, so that means we have y cubed left over. And that has been factored using the GCF. Let's look at number 3. So we have 6m to the fourth plus 18m to the fifth n squared. So again, we look across and say, what is the greatest integer that we have that can be divided out of both? And these both have a factor of 6, so we have a 6. We can take an m to the first power out of both, and we can take an n squared out of both. When we do that, we're left with 6 divided by 6 is just 1, m divided by m is just 1, but n to the fourth divided by n squared, when you're dividing like bases, you subtract the exponents. So 4 minus 2, so we just have n squared left over. Then we have our plus 18 divided by 6 is 3. M to the fifth divided by m to the first. 5 minus 1 is 4. And then we have n squared divided by n squared, and that's just 1. So there it has been factored by taking out the greatest common factor. Okay, scrolling down the page a little bit, let's look at number 10. What is a perfect square? A perfect square is a number whose positive square root is a whole number. You can check out that definition on page 21 of your textbook. So number 11, how many perfect squares do you have memorized? Well, you can fill those in on your own time. So let's take a look. Is x squared a perfect square? Or y squared? Or 16x squared? Well, if the definition is where a positive square root is a whole number, or in other words, when you take the square root, you get a pretty answer. Well, then x squared is a perfect square because the square root of x squared is just x. So yes, the square root of x squared is x, so that looks nice. The same thing for y squared. The square root of y squared is just y. And the square root of 16x squared, I'm sorry. Well, the square root of 16 is 4, and 16 is a perfect square. And the square root of x squared is x. So 16x squared is also a perfect square. So x squared, y squared, and 16x squared are all perfect squares because we can take the square root of them nicely. So what is a difference? Of course, you've heard of a difference before. It's just whenever you are using subtraction. But for a difference of two squares specifically, it would be a polynomial of the form a squared minus b squared, which could be written as the product of a plus b times a minus b. And if you want to look at that definition in your book, that's on page 336. So if we want to give an example of the difference of two perfect squares, how about x squared minus 25? This is just one example of course, an endless number of possibilities. But it's a difference because of that minus sign in the middle. X squared is a perfect square, and 25 itself, you just ignore the sign, is a perfect square. So that's a difference of two perfect squares. So why do we look at that? Well, the difference of two perfect squares will always factor, but not if it still has the GCF in it. Factoring out the GCF is always the first rule of factoring, and it will factor into conjugates. So for example, x squared minus 25. Well, you get x plus 5 times x minus 5. These two are conjugates because they look the same except for the sign in the middle is opposite. So the factors x plus 5 and x minus 5 are conjugates, binomials with the same first term and last terms, with the same first term and the last terms are opposite. So how are the first and the last terms of the binomials found? Well, you notice that the first term of each is x and x. Well, those squared, x squared is what we started with. So the square root of x squared is how we got the first term, and the square root of 25 is how we got the second term, and then we just had opposite signs. So just to make sure you're realizing that it always needs to be opposite signs, whenever you factor out, when you FOIL out x plus 5 times x minus 5, so first we have x times x, which is x squared. Outside minus 5x, inside is plus 5x, and last is negative 25. Well, the negative 5x and the positive 5x cancel, so you're just left with that x squared minus 25. That's why this only works for the difference of two perfect squares, because if we had x squared plus 25, and we wanted to factor that, well, the only factors of positive 25 would be positive 5 and positive 5, or negative 5 and negative 5. Well, if we tried x plus 5 times x plus 5, we would get x squared plus 10x plus 25, and that's not the same thing. So that doesn't work. And if we do x minus 5 times x minus 5, you get x squared minus 10x plus 25, and that doesn't work either. So the only time that we can factor where the first and the last terms are the same but the sign in the middle is opposite is when we have a difference of perfect squares, not when we have a sum. So let's just look at a few examples here. On number 16, we have x squared minus 121. So knowing the pattern that we know, we can put our parentheses already. And by the way, always check first to see if the GCF has been taken out. There are no greatest common factors between x squared and 121, so we're good to go. So the square root of x squared is x, and the square root of 121 is 11. And then you just make sure they're conjugates. So we have a plus in one and a minus in the other. The order of the plus and the minus sign don't matter. On number 17, again, check to see if there's a GCF that can be taken out. Well, we can take a 3 out of both of these. So first, we'll factor out the 3, and we'll be left with y squared minus 16. So now we have the 3 in the front, and now we have a difference of 2 perfect squares. So to factor this completely, we'll have 3, and we can leave that there and then do the difference of perfect squares like we did before. The square root of y squared is y, the square root of 16 is 4, and we put the opposite signs. And one more example. Let's look at number 19. We have x to the 4th minus 81. There isn't a greatest common factor to take out, but we already have a difference of perfect squares. So the square root of x to the 4th is x squared. The square root of 81 is 9. And then we need to have opposite signs. But are we done here? No, we're not. Check out this second term, x squared minus 9. That again is a difference of 2 perfect squares, so we need to factor this one more time. So we'll get x squared plus 9 times the square root of x squared is x, square root of 9 is 3, and then the opposite signs. Now that has been factored completely. So we get x squared plus 9, x plus 3, x minus 3. Okay, so let's look at factoring trinomials with the constant term c is greater than 0, and the leading coefficient is a equals 1. So just so you remember, this is ax squared plus bx plus c. So that c that they're talking about is greater than 0. That's this 12 in this example. And the a equal to 1, that's just the coefficient in front of the x squared. So here's an example of x squared plus 7x plus 12. And this is a trinomial because there's 3 terms in our expression here. So whenever we're factoring trinomials, we look at what 2 numbers multiply to equal 12 and add to equal 7. So number 29 says, if the constant term c is positive, the signs in your 2 factors will be the same. Why is that? Well, if the constant c is positive, we get that from multiplying the second terms in each of our binomial factors. So if the last number is positive, that's because the only time you can have a positive product is because a positive times a positive equals a positive, or a negative times a negative equals a positive. And on number 30 here, it says, what will determine whether the 2 signs of your factors will be plus or minus? Well, it's the middle term. If c is positive and b is negative, both are going to be minus. If c is positive and b is positive, both factors will be plus. So if we look at this example, factoring the following trinomials, let's look at number 31. So to factor this trinomial, we're looking at the last term 11, and we're saying what factors of positive 11 add up to negative 12. I'm sorry, positive 12. So we're saying what multiplies to positive 11 but adds to positive 12. Well, the factors of 11 is prime, so that means only 1 and 11 are factors of 11. So 11 plus 1 is 12. So those must be the second terms of our binomials. Looking at number 32, here we have x squared plus 16x plus 39. What multiplies to 39 but adds to 16? Well, 39 is the same thing as 13 and 3, and 13 plus 3 is 16. So those are the factors. X plus 13, x plus 3 are the binomial factors for x squared plus 16x plus 39. And then 33, we have x squared minus 7x plus 6. So what are factors of positive 6 that add up to negative 7? Well, for 6, we have factors of 6 could be 1 and 6 or 2 and 3. But be careful about which ones you choose here. So if we have 6, if we multiply -1 times -6, those two numbers add to -7 but multiply to +6. So looking at a trinomial with a constant term c that is negative and the leading coefficient is still 1, it's really similar, but let's look at number 47. If the constant term c is negative, the signs in your two factors will be different. Why is that? Well, in multiplication, if you have a negative product, you can only get that by multiplying a positive times a negative. Therefore, our two binomials must have, one of them will have a plus sign and one of them will have a minus sign. So let's check out number 48 here. We have x squared minus 9x minus 10. So now we have to think, what are the factors of -10 that add up to -9? And remember, one of them will be addition and one of them will be subtraction. So one will be positive, one will be negative. So you have to think, what positive and negative numbers multiply to -10 but add to -9? Well, -10 we can get by multiplying -10 times +1, and -10 plus 1 is -9. Let's look at number 49. We have x squared plus 8x minus 9. So again, what factors of -9 add up to +8? Well, here, because the 8 is positive, that means the bigger number will have to be the positive number. So we can get +9 and -1. So 9 times -1 is -9, and 9 plus -1 is +8. And then number 50, we have x squared plus 7x minus 18. So what factors of -18 add to +7? And again, we'll have different signs. So to get factors of -18, well, for 18 itself, if we look at 9 and 2 will get us 18, but if we want the signs to be correct, then we need a +9 and a -2.